This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to talk about heat and specific heat capacity. In our last video, we talked about thermal energy, and we also talked about temperature. Remember that thermal energy is the total potential and kinetic energy of all the atoms and molecules in a substance. And remember that those molecules have that energy by motion. So they're either moving around or rotating, or in the case of a solid, they're vibrating back and forth. Let's also just remember the difference between thermal energy and temperature. Remember that temperature is a measure of the average kinetic energy of the molecules and atoms that make up a substance, whereas thermal energy is the total. In this video, we want to talk about heat. So how does heat relate to thermal energy? Well, heat is simply the word we use to represent the transfer of thermal energy. So in the diagram here, we have a warm object next to a cool object, and we know that energy will be transferred from the warm to the cool, and that's what we call heat. So heat is simply energy in transit. So thermal energy moving from one object to another, that's what we call heat. Let's think about one of the things we know about heat just from our own practical experience. Heat always goes from a higher temperature object to a lower temperature object. Imagine how weird it would be if, when you put a warm object next to a cool object, that the warm object got warmer and the cool object got cooler. And obviously we just don't see this. So heat always goes from higher temperature to lower temperature. Now, we can make it go the other way, but that requires putting in energy. So in other words, if you think about how a refrigerator works or an AC unit works, there we can do it, but it requires us to expend energy to make that happen. It doesn't happen naturally. So just some examples of experiencing that transfer of thermal energy. You know, if you touch something that feels warm, you can feel your hand absorbing that thermal energy. Or if you touch something that's cool, you can feel your hand is losing thermal energy to that object. Well, that's what we mean by heat. So either heat is going into your hand or heat is leaving your hand. One of the things I'm sure you've experienced is that certain objects seem to stay hotter a lot longer than other objects. And we can say that they have more thermal inertia. Remember, the word inertia we used originally to refer to the fact that an object in motion wants to stay in motion, or an object at rest wants to stay at rest. And we saw that the more mass an object had, the more inertia it has. It's harder to get it moving or to stop it than if an object has less mass. So here we can talk about thermal inertia. And here's an example. You've probably all done something like this with similar foods. But when you take toast out of a toaster oven, it's usually at about 400 degrees, and that'd be 400 degrees Fahrenheit. Let's say you also heat up some soup on the stove and you heat it until it's boiling. That would be at 212 degrees Fahrenheit. Initially, the toast is definitely at a higher temperature. But let's say that you wait 30 seconds after the toast has come out of the toaster oven and the soup has come off the stove. You know you're a whole lot more likely to burn yourself on the soup. And that's because it has more thermal inertia. It holds on to that energy longer than the toast does. So let's talk about how we can quantify this concept of thermal energy. We do that by defining something called specific heat capacity. We abbreviate specific heat capacity with the letter C, so that's how you're going to see it represented. And the specific heat capacity is defined as the quantity of heat required to change the temperature of a unit mass of the substance by 1 degree Celsius. So what does that mean? Well, what that means is that if I have, let's say, a block of a material, and let's say that I have a 1 kilogram block, the amount of heat that I have to add to that material to get the temperature to change by 1 degree, so let's say to go from 20 degrees to 21 degrees Celsius, that is the specific heat capacity. And so you'll notice that it has units of joules, the amount of energy I need to add per 1 kilogram per degree Celsius. Here are some different specific heat capacities for some different materials. You'll notice that water has a very high specific heat capacity. And therefore, you'll notice that whenever your food has a lot of water content, it both takes a lot of energy to get it heated up, but it also then takes more time for it to cool down. So let's look at an example of that. Does a substance with a higher specific heat capacity take more or less time to cool down? Well, I think you can probably guess that the idea is that if the specific heat capacity is higher, it takes more time to cool down. And let's just think of an example. Let's say that I have 1 kilogram of water, and I also have 1 kilogram of iron. So I've got a block of metal, and I've got, let's say a cup filled with water. Since water has a specific heat of 4,196 joules per kilogram degree Celsius, and iron has a specific heat of 449 joules per kilogram degree Celsius, you'll notice that the iron only has to lose 449 joules to cool off by 1 degree, whereas the water has to lose almost 10 times that amount of energy to cool off by the same amount, and that's obviously going to take more time. So, how much energy does it take to raise the temperature of an object by an amount delta T? Well, here we're going to build on that concept of specific heat capacity. We define Q to represent the energy or the heat that is either going in or out of the object, M is the mass of the object, and C is the specific heat capacity of the material, and finally delta T is the change in temperature. So you'll notice that the amount of energy that's either added or taken away from the object is Q, so that would be in joules. And we'll just check our units here and make sure they work out. We know that mass is a unit of kilograms. Specific heat capacity, we said, has units of joules per kilogram per degree Celsius. And then delta T, our temperature change, is going to be in degrees Celsius as well. And so you'll notice that kilograms cancels with kilograms, degrees Celsius with degrees Celsius, and we're left with joules on the right-hand side. So at least from the point of view of units, that formula makes sense. By the way, this formula can be used whether we're adding or taking away energy from the object. In other words, whether the object is heating up or cooling down. So if cooling down, then both delta T and Q are going to be negative. And so a negative Q just means that we're taking energy away from the object, or that object is losing energy, as opposed to when it's heating up and gaining energy. So let's try an example with this formula. How much heat does it take to raise 2 kilograms of water by 5 degrees? In this case, we need one other piece of information, which we looked at a few moments ago, and that is that the specific heat capacity of water is 4,196 joules per kilogram per degree Celsius. So we know we need to know that. That's C. Notice that we've got the mass here, m, and the temperature change, delta T, is 5 degrees. And so in this case, we can just plug into the formula. The heat is equal to mc delta T. So that's the mass of 2 kilograms times the specific heat capacity, 4196, times the temperature change of 5 degrees. And if you calculate that, you should get 41,960 joules. Remember, one of the points that we made in an earlier video is that the joule is a relatively small unit of energy. So 2 kilograms is not a lot of water, and a 5-degree temperature change is not a huge temperature change, but that requires a lot of heat in joules because a joule is not a very big unit. Also, we might want to rewrite this in scientific notation just for practice. So 1, 2, 3, 4. So that'd be 4. I'm going to just round it to 2 significant figures here. So 4.2 times 10 to the 4th joules would be our answer. Okay, let's try another example. A 3.5 kilogram block of iron loses 2.5 times 10 to the 3rd joules of heat. What will be the change in temperature? So first of all, we know that we need the specific heat for iron. So that's 449 joules per kilogram degree C. And we can see here that what we've been given is we've been given Q. We have to be a little bit careful about that. You'll notice that since it's losing that, we'd want to say that Q is negative 2.5 times 10 to the 3rd joules. And therefore, our delta T is going to come out as negative because it's losing temperature. You'll also notice that what we're trying to find is delta T. And so the first thing we're going to do is rewrite that equation algebraically for delta T. So let's do that part. Q is equal to mc delta T. And since I want to solve for delta T, I'm going to divide both sides by mc. So the m's cancel out and the c's cancel out. And you'll notice that I get that delta T is Q over mc. So at this point, I can now plug in the numbers. Delta T is equal to negative 2.5 times 10 to the 3rd joules. So again, I'm calling that the amount of heat negative because it's losing that amount of heat, divided by the mass, which is 3.5 kilograms, which we have up here, and then divided by the specific heat for iron, which is 449 joules per kilogram degree C. If you work that out on your calculator, you should get that delta T is equal to negative 1.6 degrees Celsius. So our object lost 1.6 degrees. It turns out that there are other units that heat is often measured in besides the joule. The joule is our SI unit of heat, or SI unit of energy. So that's normally what we're going to use. But the unit of the calorie is frequently used as well. And so let's look at what the conversion is. 1 calorie is equal to 4.18 joules. So let's do a practice unit conversion here. Convert the heat from the previous problem from joules to calories. So in our last problem, we found that the heat was, or we were actually given, that the heat was negative 2.5 times 10 to the 3rd joules. Remember, when we do a unit conversion, we're just going to put parentheses here, and we're going to take our conversion factor and stick it in there. We want to get rid of joules, so that's how we know that joules goes on the bottom. and calories goes on the top. And so if we look at that, we can see that we have successfully canceled joules. And we just have to take that negative 2.5 and divide by 4.18. And when you do that, you should get negative 598 calories. So you'll notice about 4 calories, or sorry, about 4 joules to 1 calorie. Now, you're probably asking this question, is this the same as a food calorie? Because we're all familiar with the concept that the amount of energy given in food is given in calories. However, it is not the same. So the calorie that we use when we talk about food, you'll notice it's always written with a capital C to distinguish it from the calorie that we were just talking about. This is a bad notation, but historically this is what's been done, so we're kind of stuck with it. And a food calorie, again with a capital C, is actually a kilocalorie. In other words, 1,000 of the calories that we were just talking about. So since we know that 1 calorie is equal to 4.18 joules, then a kilocalorie, or a food calorie, is 1,000 calories, or 4,180 joules. So a food calorie is 1,000 times bigger than a regular calorie. Let's try a question that illustrates why it's so hard when we want to lose weight. And that is that a calorie, in terms of a food calorie, it's a big unit. And so let's see, how many calories do we burn by lifting a 10 kilogram mass, 0.5 meters, for a total of 30 times? Now, in case you have a little trouble still thinking about what is a kilogram, 10 kilograms weighs about 22 pounds. So imagine that you're at the gym and you take that 22-pound weight and you lift it up and you do that 30 times. So the first thing we want to do is calculate the work to lift the weight once. You'll notice we have to calculate what the force is that we're exerting. Remember that if I've got an object and I want to lift it up at a constant velocity, the force that I exert is the same as the weight of the object. And we know we can calculate the weight of the object as mg. So again, remember here that this means weight. It's a little confusing because we're about to use W to mean work. So let's first calculate the weight of the object. That's 10 kilograms times 9.8. And so the weight of the object is 98, and that's newtons. So once we know the weight of the object, we know that the force we have to exert is also 98 newtons. And now we can calculate the work done to lift that weight by a certain distance. So we know that work is F delta x, and in this case the force is 98 newtons, and we're going to raise that half a meter. And what we get is work of 49 joules. Remember that it's joules because work is energy. So now it says we want to do that 30 times. So the total work doing this 30 times is just going to be 30 times 49. So then the work that you would do total would be 1,470 joules. Well, let's now see how many calories did you burn in doing that exercise. What we want to do is convert to food calories. And remember that To distinguish a food calorie, we use a capital C there, so that means food calories. And we just learned that there is 1 food calorie in 4,180 joules. And so what we want to convert is that number we just came up with, which is that we do 1,470 joules of work in lifting that mass 30 times. Well, you can see it's not looking too good here. When you do that conversion, what you end up with is 0.35 calories. We didn't even burn 1 calorie. So we didn't earn, that Snickers bar or whatever. And that makes me kind of sad because I wanted that Snickers bar. By the way, one thing that's really interesting, if you have some kind of a fitness tracker, and so for example, I have an Apple Watch, but obviously there are lots of other ones out there. But you may have noticed that it will tell you about 2 things. It will tell you about active calories, and it will also tell you about total calories. So in other words, what are the active calories you've burned versus what are the total calories you've burned. The good news is that just by sitting and doing nothing, we burn almost 2,000 calories a day, and this is food calories we're talking about. So when you do activity on top of that, you are burning additional calories. And it used to be fitness trackers would give you the total calories, and so you always thought you were doing more than you really were because a lot of those were just because you're living during that activity and burning those calories just to keep your metabolic processes going on. But it's kind of nice now that they'll show you what the active calories were. That's how many calories did you burn on top of what you would have burned if you had just been sitting there and reading a book. So anyway, it's kind of interesting. In our next video, we're going to continue looking at the topic of heat, and we'll talk about something called heat of fusion, which is the heat it takes to change a solid to a liquid. And we'll also talk about the heat of vaporization, which is what it takes to change a liquid into a gas.